Hello everyone, thanks for having me in this session and apologies for not being able to make it in person today. Of course, I'm happy to answer any questions that you might have via email. So this is a joint project with Fadi Anton and Gary Froyland from the University of New South Wales on the sensitivity of finite-time coherence sets. So what are finite-time coherence sets? Let's look at a time-dependent flow field, a time-dependent vector field, in this case in the plane. And what you see here are a bunch of particles that are evolved according to this flow field. And if you stare at this for a couple of seconds, well, then you observe these regions of particles which stay close to each other for quite some time, in contrast to other regions which disperse. So in fact, what we're looking for are these sets, these gray sets here, or the black set. In contrast to the blue one, they don't disperse, they stay coherent. And so this is what we're interested in. In fact, what we're ultimately interested in is how they change if you vary some external parameter in your system. So first of all, how do you model this? How do you describe precisely mathematically what a coherent set is? Here's the idea in the non-autonomous context. Again, almost invariant sets. So some set is called almost invariant if the probability that you map from the set into its complement is small. So any set for which this is small is called almost invariant, or in the time-dependent context, it's called a coherent set. This particular work by Gary generalizing this idea to the non-autonomous case. Now, if you add a little bit of diffusion to your map, if you convolve it, for example, with a dispersion kernel, then it's not too hard to see that this transition probability for the perturbed map is up to first order bounded by the length of the boundary divided by the volume of the set times epsilon. And then the nice observation by Gary a couple of years ago is that this is actually a classic problem, the so-called isoperimetric problem, phrased a little bit differently here. And the solution, of course, is the disk. Now, there's a nice connection between the isoperimetric problem and a Laplace eigenproblem. Namely, if you describe your set as a sublevel set of some level set function, then you can rewrite this isoperimetric ratio in terms of this ratio of between the gradient, between the L1 norm of the gradient and the shifted L1 norm, or the L1 norm of shifted version of U, which then is approximately equal to this Rayleigh quotient here. And the Rayleigh quotient, this Rayleigh quotient here is the second eigenvalue of the Laplace eigenproblem. So in essence, the idea is if you look at the Laplace eigenproblem and compute the eigenfunction corresponding to the second eigenvalue, then by looking at the sublevel set of this eigenfunction, you get a set which is approximately the optimizer for the isoperimetric problem. Now, Gary generalized this to the dynamic context by saying, well, we don't have a single fixed set, we have a whole family of sets. So starting with some set S, we evolve that by the flow map, yielding a time-dependent family of sets, ST. And what we're looking for are sets S for which this entire family is close to a minimizer of the isoperimetric problem. So for example, you could say, well, I'm trying to minimize the average of the isoperimetric ratio of this time-dependent set S. Now, in the volume preserving or the area preserving case, so let's assume that the flow is area preserving, we can approximate this integral here, this average, by this time discrete average, so to speak, yeah, simply by looking at the ratio, taking the average of the isoperimetric ratio at the initial time and the final time. So what we need to approximate here is the boundary length of the set at the final time. Yeah, well, the boundary length at the initial time is simply given by the squared L2 norm of the gradient of u. In order to get the same thing at the final time, we need to look at the push forward of u under the flow map, yeah, which is given by applying the transfer operator to this level set function u. Yeah, so the transfer operator is describing how, well, in general, probability densities evolve with the flow. In our case, this is the level set function u. Okay, and we finally end up with this approximation here for the dynamic isoperimetric ratio, yeah, involving the level set function and its push forward under the flow map, which now is very similarly to the static case, simply the second eigenvalue of this dynamic Laplacian here, which involves the transfer operator and its adjoint, which of course is simply the Koopman operator. Now again, the idea is the same as in the static case. You compute the eigenfunction at the second eigenvalue and then a coherent set, yeah, which is the solution of the dynamic isoperimetric problem, is approximately given by a sublevel set of that eigenfunction. Now, in order to solve this eigenproblem numerically, we're going to use a finite element approach, and for this we need the weak form of that eigenproblem, which can be derived in the classical way. So you multiply by a test function, you integrate, you use the theorem of Gauss with an appropriate boundary condition, and you end up with this formulation, which can further be rewritten in terms of the Cauchy-Green deformation tensor, yeah, by transforming back to the original domain. Now, if we define this averaged deformation tensor here, then the original strong form of the problem, including the boundary conditions, which are missing here, is equivalent to this weak form here of the eigenproblem, where this bilinear form A is given by this integral involving this averaged deformation tensor. Now, in this study, we're really interested in how coherent sets depend on an external parameter epsilon. Yeah, so we're considering the case of we have a whole family of maps depending on this parameter epsilon here. You know, for example, if the vector field that is given depends on epsilon, or another interesting case is that time is actually viewed as the parameter. Yeah, we assume this dependence to be smooth, so this yields a whole family of eigenproblems. And then the question is, given some eigenpair at some depending on epsilon, what's the derivative of the corresponding eigenfunction with respect to this parameter? Now, this will ultimately yield how the sublevel sets of this eigenfunction depends on epsilon as well, and enable us to predict the change of some coherent set with respect to epsilon. Now, the first observation is that one can actually explicitly compute the derivative of the averaged deformation tensor, which is given by this expression here. And if we use this in order to define a corresponding bilinear form, then this bilinear form is actually simply the derivative of the original bilinear form with respect to the parameter. Now, it turns out that the linear response, or more precisely the derivative of the eigenpair, can be computed as the unique solution of a linear system. Yeah, so here it is. Yeah, maybe it's more instructive to actually look at the corresponding strong form. Yeah, so we have this linear system involving the eigenfunction itself, involving the corresponding eigenvalue, yeah, and then using this matrix. Well, you can first of all you can compute the derivative of the eigenvalue, yeah, by evaluating a dot at the second eigenfunction, yeah, and then you solve this linear system here, which gives you the derivative of the second eigenfunction. So that's pretty straightforward. Here is the discretization approach via finite elements again. So again, as I outlined, you start with the dynamic Laplacian eigenproblem. You derive the weak form. Yeah, and now by a standard Ritz-Galerkin idea, simply by considering a finite dimensional subspace of your original function space, you end up with this generalized eigenproblem with a stiffness matrix K, depending on the parameter, and the mass matrix M. Yeah, these are involving certain integrals using our the finite element basis functions as usual. And similarly, from the linear system for the linear response, you get this corresponding linear system for its finite element approximation. Yeah, so essentially the only thing that needs to be computed additionally is this, well, linear response matrix L here, as one might call it, which is simply given by the evaluation of the derivative of the bilinear form on all finite element basis functions. Yeah, so here's a first example, the standard map. Yeah, simply a diffeomorphism on the flat 2 torus, and we're perturbing the nominal parameter here a little bit. Yeah, and then using a standard finite element scheme here, this is what you get. So this is the second eigenfunction. This is its derivative with respect to epsilon. And if you now try to predict the eigenfunction at the value at the nominal at the perturbed value of A, yeah, so the nominal value plus 0.5, which is a pretty pretty large deviation, then you end up with this, which is at least visually pretty similar to the exact eigenfunction at that perturbed parameter value. So that seems to work pretty well in this case. Yeah, here's a comparison between the corresponding level sets. So the black line is the sublevel set, is the coherent set, a certain coherent set at the nominal parameter value, and the red dotted line here is the level set for the true perturbed eigenfunction, and the green one is the prediction using the linear response. And as you can see again, this is pretty well in agreement here. So again, emphasizing the advantage here is that you can, by a single computation of the linear response, you get a pretty reliable prediction of how the coherent sets change with respect to the parameter, even for rather large parameter changes here. Now, a second example, two gyres on the unit square rotating in opposite directions, yeah, and over the time interval under consideration, these two gyres rotate by 90 degrees. Here's what you get with our approach. So that's the second eigenfunction. That is its derivative with respect to the parameter. And, sorry, I forgot to mention the parameter is time here in this case. Yeah, so we're interested in how coherent sets will further change in time if you increase time further. Yeah, and you end up with this prediction here, which again is at least visually pretty similar to what you obtain if you compute the exact eigenfunction at the new parameter value. Again, here is how the coherent sets change, the level set evolution. Yeah, so in black, the original one, and then red is the exact change, and green is the predicted change by the linear response. And again, except for this region down here, the prediction is pretty accurate. Now, let me show you how this whole thing can finally be implemented using data only. Yeah, so in the approach that I presented so far, what you have to do is to numerically integrate the averaged deformation tensor. This can be avoided by explicitly approximating the transfer operator. Yeah, so we're now going to approximate the action of the transfer operator on some finite element basis function, yeah, by a linear map, by a matrix alpha here. Yeah, so and for this to work, we need two bases, two finite element bases, one at the initial time and one at the final time. And if we do that, then the stiffness matrix of the discretized eigenproblem will be given by the average of the original stiffness matrix at the initial time and by this transformed stiffness matrix involving the approximate transfer operator. So how do we approximate the transfer operator? Well, one approach is to do this by collocation, yeah, namely by requiring that the approximation, yeah, so this linear combination of the basis functions at the final time is actually exactly equal to the value of the push forward of some basis function at certain nodes. Yeah, so these are nodes on a grid or randomly scatteredly chosen at the final time. Now, if we do that, then using the fact that we typically use a nodal basis for the basis functions, yeah, then we end up with the coefficients of the matrix of the transfer operator simply being the basis functions at the initial time evaluated at the pre-images of the nodes at the final time. Now, this is nice because it's easy to evaluate, but we need the inverse of the flow map, which in the data case is not really available. Yeah, so the next idea is to simply choose, the nodes at the final time as the images of the nodes at the initial time under the flow map. Well, if we do that, then these coefficients simply turn out to be 0 or 1, depending on whether this is the node corresponding to the basis function or not, meaning that the approximation matrices for the transfer operator is simply the identity matrix. Yeah, so in some sense, we have a trivial approximation for the transfer operator because we have put the information about the dynamics into the choice of the FEM grid. Now, so this is nice for the stiffness and the mass matrix. How does this work for this stiffness response matrix? This matrix capital L, yeah, which as we've seen is this A dot this A dot a bilinear form evaluated at the basis functions. Well, this is simply given by this integral here, yeah, and this integral is again can be approximated by this integral here involving the gradients of the basis functions and this matrix here. And this matrix involves certain derivatives of the basis functions as well as evaluations of the derivative of the flow map at the nodes, at certain nodes. So here's an example. On the left-hand side, going back to the rotating double gyre example, on the left-hand side there's the eigenfunction corresponding, computed using the quadrature-based method. We need on the order of 10 to the 5 time integrations here, because we need that many quadrature points in order to reasonably accurately approximating the integrals. Whereas in the database approach, we get away with 10 times less data points, yielding a pretty good approximation to this second eigenfunction as well. All right, here's the preprint. If you're interested in reading more details about the study. We also provide an implementation in MATLAB within the FemDL package. You can download that on GitHub. The basic finite element approach is also implemented in the coherent structures package by Daniel Karash and co-workers. The linear response stuff is not in there yet, but that's going to come soon. All right, thanks very much for your attention. Again, I'm very sorry that I couldn't attend live. Again, I'm happy to answer any question via email. Take care and bye-bye.